Steve Sandler, the founder of AEi Systems, a company that specializes in modeling, analysis, and simulation. A large part of our focus is on analog and power electronics, though we support RF and instrumentation as well, primarily for the high reliability arena. In our business, we are frequently called on to assess and troubleshoot system-level issues, many of which are related to the power distribution network. The problems we tend to encounter are generally related to issues such as noise, PDN-type transients, clock problems, and EMI. The causes of the customer issues are generally covered in this very short list: stability, EMI, switching issues, distribution issues, and subpar performance. In this presentation, I'll focus on the issue of control loop stability. This is a critical subject because in our experience at AEi Systems, we have found that most system-level problems are eventually traceable back to stability issues. We don't care about stability as a number, we care about how it impacts performance. There are 4 propagation paths, 5 if we count air transmission, that we are interested in investigating in distributed power systems. PSR is the path from the intermediate or input bus through the regulator to the output. Internal ripple and noise are the second contributors. Dynamic load demand, which mixes with the regulator output impedance, presents a third path. And finally, there's a reverse transfer crosstalk path from other regulators in the system. One of the major conduits for the degradation due to these paths is poor control loop stability of the various regulators and other circuits. In this chart, we can see the impact of stability on the reverse transfer of a regulator control loop. Reverse transfer is the current appearing at the input of the regulator as a result of load current variation. In most linear regulators, this ratio is 1 at low frequency. Note that at 13 degrees, the reverse transfer shows a gain of nearly 4, meaning that 100 milliamps of load variation will appear as 400 milliamps at the input bus if it's at the frequency of poor stability. In a similar fashion, a 13-degree phase margin represents a 30 dB loss of PSRR at the frequency of poor stability. It's not an accident, nor is it random, that I chose 13 degrees as an evaluation point. I selected this point since it's representative of the performance we typically see for linear regulators and voltage references operating in various applications. Point of load regulators, or POLs, tend to have better phase margin but have other stability issues. Op-amps, especially unity gain op-amps, often have poor phase margin as well, and this is often exacerbated by highly capacitive, multi-layered printed circuit board designs. An interesting side note is that most of our customers tend to modularize their designs. This puts the bandwidth of the multiple converters at the same frequency, causing the poor PSR of one regulator to coincide with the poor reverse transfer of another, creating a perfect storm. So why are we so concerned with the overall stability of the control loop? After all, while 13 degrees may ring a bit, it won't oscillate and it does offer fast response. We care because all closed-loop system performance is controlled by stability, and in particular the open loop to closed loop transformation due to the gain vector t, 1 over 1 minus t. In this image we see the response to a small current step applied to a voltage reference with an output capacitor. This ringing appears to be damped and at a single frequency for each edge. However, looking at the spectrum plot, the results show that there are many frequencies present. Any place in the system where there is a high impedance at one of these spectral frequencies, noise voltages will appear. In our work at AEi Systems, the single largest percentage of issues we solve is directly or indirectly related to poor stability. In almost all cases, we find linear regulators and voltage references to have poor stability, and this is due to the lack of information regarding the stable performance of these devices. We discussed this issue at length in an article titled Simple Method to Determine ESR Requirements for Stable Regulators, which appeared in Power Electronics Technology magazine. The article uses a single measurement to define stable solutions, even for a particular phase margin. Here's an example that shows the effect of a linear regulator's instability on an application. In this example, we're measuring the impact of the stability of an LDO on clock phase noise or jitter, and we're directly measuring the phase noise or jitter of the clock using a signal source analyzer to measure the phase noise of the clock. Note that we are showing the clock's phase noise with 2 different voltage regulators, one of which is more stable than the other. In the measurement where the clock is powered by the less stable LDO, the clock's poor phase noise near the frequency of the LDO's poor stability is easily seen in the phase noise plot, showing clearly how the regulator's instability significantly contributes to the jitter. The propagation of noise due to the voltage regulator stability is not limited to clocks. We also see similar issues in low noise amplifiers and instrumentation circuits as well. For those interested in learning more about voltage regulator stability, please see this article. And if you have any questions or comments, please feel free to email me at steve@picotest.com. And thank you.